なんといってもインパクターですね。これはね、この次は順番が次っていうだけじゃなくて、インパクターの話はもう世界中どこもやったことがない初めてのものなので、これはね、スタッフの皆さんは緊張とそれから楽しんでほしいと思いますよね。最初にやる人だけが感じられるそういうその気持ちというのを大いに楽しんでプレーしてほしいと思ってます。
それは福祉愛組合シフト1の訓練を行います。
このバス、ゲート1ですね、で降下開始ですが、次のシフト以降で、順次降下原則、ゲート2、であとは明日の、午前中のシフトで、ゲート3、合の合判断等を行っていきます。で合判断が出た後は、合コマンドとプラスアルファの計5コマンドを送って、あとは探査機にお任せという状態になります。
はやぶさ4号機じゃなかったら運用なので、また自由に発展を運用ですので、気合い入れて頑張りましょう。
これは本当にはやぶさ2としてというのは本当に人類として初めてのことになりますので、しっかりやっていきましょう。まずはゲート1を平和に聞こえます。よろしくお願いします。
それでは以上、現時点で終了したいと思います。一のチェックは、はい、それでは、ESL が、グリーンですね。はい、UDSG、はい、グルーです。はい、エステッドシップ、はい、エステッドシップ、グリーンです。それでは、現在では、じゃあゲート1に関してはグリーンということで、今、コートしたいと思います。はい、了解です。はい。
オプションもう内内に移してしまう。今とりあえず何が起こるか分からないですか。もうこのまま平和に内内に移しちゃうかな。内内じゃあ今日決めましょうか。どうしよう。早くやりたいな。次カメラにこうドーンと使う。そこまで内内が持たなかったらじゃあアボートになっちゃうので。そこまで持たすんですよ。それはちょっと、それは全然保証できないからですよ。できるよ。いやいや、だからカンベラにスイープで移そう。じゃあ、22時30分 に、キャンベラに移します。理由は向こうを認識してない。オペレーターとしてはないですか。
最初は認識しなくてこっちから行ったんですけど、聞いたらなんかいろいろ確認して、なんかエラーフラグが立っていて、それをリセットしたらおそらくオペレーショナルになるんだろうって言って、100% シュアじゃないって30分かかるって言ったんですけど、実際リセットしてみたらすぐにリセットできてオペレーショナルになりましたね。
になりましたので、シフト4の、ブリーフィングを開始したいと思います。
この後の流れですが、0時45分ゲート3の確認開始ということで最終確認を行って、GO の場合はなるべく早くGO送信、今回は5コマンド GO 送信に合わせて送るコマンドがありますので、なるべく早くコマンドを送っていくということになります。
試合分離から試合の起爆までが、40分2400秒になっていますので、基本的に地上から手を入れる隙はありません。でもう AOCS としても NEC さん、JAXA 含め、基本的にはかなり検証、実験等をやって、自信を持って臨んでいますけれども、この試合分離から起爆までの4回のデルタ部位のうち、3回は20秒噴射が実施されることになります。これは、Hayabusa2 としては過去最大が10秒噴射でしたので、その2倍噴射するという形になっていまして、自信はあるけど安心はできない。何か起こった際には頭を切り替えて次の動作にすぐに移れるように皆さん気を張っておいていただければなと思います。で、泣いても笑っても1回きりの夢になりますので、楽しんでいただければと思います。
はい、これもHayabusa2としては10年越しの実験というか、もう10年前から準備して、いよいよこの本番の日が来ました。今日SCI 関係とか DCOM 関係たくさん開発から携わっていただいた方も来ていただいてますけども、その昔起こったことも含めて思い出しながら、なんかお気づきの点があればすぐ共有していただくようにお願いします。いい結果が迎えられるように頑張りましょう。よろしくお願いします。
今日の3時間のために今までの年月全部費やしてきたので、私だけじゃなくてたくさん理学が見えるんですけども、DCOM 側も基本的にはもうシーケンスタイムラインに従ってとにかく進んでいくだけで我々何も手を出すことないので、邪魔にならない範囲でカウントダウン等をして、皆さんと情報を共有したいと思います。はい、遂行できるように皆さんに願っています。
それでは、いよいよお楽しみの時間なので、皆さんで楽しんでいきましょう。ではよろしくお願いいたします。よろしくお願いします。
集計を行いたいと思います。サイエンスはどうでしょうか。グリーンです。DCOMサイエンス、SCI サイエンスいいですか。はい、DCOM の SCI も。はい。SCI グリーンです。はい。DCOM、はい、DCOMいいですね。グリーンとでいただけますでしょうか。グリーンとさせていただきます。はい、それでは、現時点でオールグリーンですので、ここの時点ではGOと判断したいと思います。フライトより袋まで。はい、はい、いよいよGOとなりました。ので、もうここは皆さんいいですね、本当に。 FD もいいですね。FD がいいってさっき言いました。はい、じゃあ行きましょう。それでは、フライトより各位、これからゴーコマンドと打っていきます。問題ないですね。じゃあ打っちゃいますよ。いいですか、皆さん。いいですって答えてください。じゃあ打ちますよ。いいです。じゃあ行きましょう。じゃあ1試合分離、送信お願いします。はい、これでもう引き換えせませんので、はい、もう信じて見守りましょう。試合分離に10秒前、9、
あと10秒で試合分離が。
7、6、5、4、3、2、1、0。PPTD から多分この後も多分いいんですけど、先から約80秒間探査機が同じ状態を保てば、ここで回避修正としたら、一連の動作が全て成功したというふうに見なしたいと思います。
電力も何も変わってないです。何も起こってないようにしか見えない。
テレメトリー検体です。新レベル正常です。はい、退避成功ですね。おめでとう。
わかんないけど、拍手していいのかわかんないです。もうなんかわかんないです。
一応、いい感のアナログにエジェクターが出してマジか。
だいぶ斜め当たってる。
いや、だけどね、外で見ると。
いやいや、まあ、なんか、まだこれ。 当たってる真ん中端自信ないわそこは
10メートルぐらいじゃなかったですか。
最初から何も映ってないよ。やっちゃった。これね。
何これピュリッツァー賞とか取れるやつですか。
緯度的には想定したところに当たって
赤道より北よりだからまさにサバース。精度いいじゃん。精度よく当たってます。01に今ちょっと赤道 GS01 当たっちゃった。喜んでくれてるのに、本当に見に行ったらみんなで怒られる。何してんの？何増やしてんだよ。
皆さんのおかげでサイエンスとしては最高のデータが取れて、小惑星というのは衝突を繰り返して壊れていったりして衝突の実は明らかにすることが大切なんですが、でそれが今回まさにできて生のデータが取れて、それをちゃんと D カムが取ってというのは最高のシチュエーションなので、ぜひ素晴らしい論文を作ってこの成果を世界にアピールしたい。本当にどうもありがとうございます。
サイエンスですね、責任者ですので、もう本当に出題実験ではですね、不十分なところをこれをですね、七でよしての夢がですね、皆様のですね、ご協力にかなることができました。本当にありがとうございます。我々頑張ってですね、いい論文を和田さんとね、香川さんと皆さんと書きますので、期待してください。ありがとうございました。
皆さん本当にお疲れ様でした。これ本当にすごい成果だと思います。タッチダウンもすごかったけど、はやぶさ2だけじゃなくて、このエシア運用ははやぶさ2だけじゃなくて、本当に人類初めての試みで、これを一発で成功させた本当にすごいです。で、はやぶさ2始まってからもう10年経ってますけど、この10年越しの実験がうまくいってよかったと思うし、ここまで来るのに工学のメンバー、それからサイエンスの方々、それからメーカーの方々ですね、本当にいいチームが作れてここまで来たんだと思います。皆さん本当におめでとうございます。はやぶさ2としてはまだ近傍フェーズでもやることあるし、帰るまでがミッションですので、まだまだやることありますけども、帰る意味がさらにできたと思ってますので、これから先も頑張りましょう。引き続きよろしくお願いします。
サイズによりけりはなんとも言えないですけど、ないよ。その枠が黒いで、ある場所はもうほぼ黒いですよ。ある場所。この画像にあるのか。ヒートまだ映らない。小さい岸が読んで、これがクレーターだ。全然違うところ。100メートルぐらいある。ドーンって。いやいや。刺さって。こっち。あの画像が見える。あれと同じのが見えるはずだよね。いやー、本当見えないかも。自信なく。もう見てる。次のやつが来てます。見えた。来た。全然見えない。まあ誰でも第一発見者なんで今だからまだ誰も発見してないです。
いやんなわけないよね。どの岩それ。
穴は小さいので。これその岩は USB 見せられないとできないですね。もっと見えない。見えてきた。超高麗の間違いされて、この色は
いやいや、これもしそれじゃなかったら坊主。多分ここに映ってる。だから1、2、3、4。これとは違う。それかもしれない。言われてみれば確かに。やめてほしい、そのテーマ。これぜひ。騙される。
はい、SV から各位へアンテナが背景から両面に切り替えました。テレビはこれからこう見えません。
ロズレベル各位、この後ですね、観測の前のデルタ V が行われます。でそれの確認を持ってゲート4に変えたいと思いますので、じゃあこの後ですね、もうタイムラインに従って観測が始まりまして、我々テレビが見れるのはおよそ1時間後になりますので、基本はもう、このデルタ V が打たれたということで、観測が落ちるということは多分ないので、食事を取るのはこの機会だと思います。皆さん、よろしくお願いします。カツカレー食いに行きました。
シフト4のブレーキングを始めます。合わせて、今回の全体のデブレーキングを兼ねて出ると思います。予定通りすべての利用テクニックを実施できまして、両方までからしてずついただきたいと思います。
いや、この時点ではどこにクレーターできてると思うので、両方を待ちたいと思います。
はい、まずお疲れ様でした。成功判定でいうと3ポイントがあって、そのうちのトッププランより上昇が確認できていることと、それからゲートボールチェックが正常ですね。だからクリティカルミー盛り上がりにはかけましたけど、クリティカルミーとしては大成功しているので、ここまでお疲れ様でした。おめでとうございます。より早めてランニングしてるので、まずお待ちしました。引き続きよろしくお願いします。
これいやこれ持ちた
それだよね。
埋まってた色が上の砂が飛んで多分出てきたんだ少しこれ出てきてねこれ表面とか
ゆっくりゆっくり。あ、出てきてる出てきてる。丸出しになってる丸出し。でもこれ後でしょ。もう一回もう一回。
多分これ前。
でもまあこれだけ近かったらだからインセクター飛んでるよ。
いや飛んでると皆さん第一発見者の近く。
ちょっと汚いよ俺。休憩してたんだよ。
佐伯さんに言って
ふざけんなよ。次がめちゃめちゃ動いてる。でもこれ明らかに確かにそこの距離広がってるんだよ。
こっちに動くのにこれだけこっちに。 下向きになって
これすげえな。ここやっぱり岩の際にはすごいねこれ。
ここも1000万。
これはもうねえ完璧じゃん。だからここら辺はやっぱ狙うべきだよね。
すげえこれ楽しいね。素敵だなこれ。これ全5ここ綺麗になってるね。動いてるね岩が。これ吹き飛ばされたよね。
でもなんか確かにちっちゃい岩はいなくなってる気がするから。
そう、それが嬉しい。
だけどなんかあそこに落とすっていうのは相当難しい。落としたい。あそこ降りたら超かっこいいよ。
もうCG の絵の通りですよ。絵に描いたようなクリエイターたちの絵の通り。
降りたい、あそこに降りたい。
なんといってもインパクターですね、これはね、この次は順番が次っていうだけじゃなくて、インパクターの話はもう世界中どこもやったことがない初めてのものなので、これはね、スタッフの皆さんは緊張とそれから楽しんでほしいと思いますよね。最初にやる人だけが感じられるそういうその気持ちというのを大いに楽しんでしてほしいと思ってます。
それは SCI の出向1のメンバーの変動を行います。
このバス、ゲート1ですね、で降下開始ですが、次のシフト以降で、順次降下減速、ゲート2、であとは明日の午前中のシフトで、ゲート3、Go の Go 判断等を行っていきます。で、Go 判断が出た後は、Go コマンドとプラスアルファの計5コマンドを送って、あとは探査機にお任せという状態になります。
はやぶさ1号機じゃなかった運動なので、また自由に運用ですので、気合い入れて頑張りましょう。
まあこれは本当にハヤブサ2としてというのは本当に人類として初めてのことになりますので、しっかりやっていきましょう。まずはゲート1を平和に終わりません。よろしくお願いします。
1号線は、はい、それでは、ESN が、はい、グリーンですね。はい、UDSK、はい、グリーンです。
Good morning, ladies and gentlemen. I'm Kuninaga. We have been very cautiously considering this launch this time, but on the July 11th, 2019, the second touchdown of Hayabusa will be now executed. Up until today, as a Hayabusa team, the second touchdown has been very seriously considered. In order to make that happen, the team members made the utmost effort, and we made a command formulation and simulation. In order to make this project a success, we had made a preparation, so it's today. We are resolved to make this touchdown a success, so that this will be leading to a momentum for the following missions. So that is something that I'm expecting as a director. The following missions means that around the Venus there is a Akatsuki, and toward the Mercury there is a Mio that is running right now. And for the future mission, the pinpoint lander Slim is currently being made. And Mars spacecraft MMX, and the fly-by emission to Disney Plus, and also Ganymede exploration juice. So these spacecrafts are currently being developed as well. So we would like to cover Mercury all the way to Jupiter for the solar planet. We'd like to start all those in the solar system, not just one spacecraft, but multiple spacecrafts will be covering the entire solar for covering the exploration of 4.6 billion years of the space. And so the new space exploration convoy will be made in that way. So that is our plan. So to the future missions, Hayabusa2, the second touchdown, will play a very important role. It's a major pivotal point and a cornerstone. So the second touchdown success or failure will be related to the testing for the successful the activities of ISAS as well as space studies in Japan. The final theme of Hayabusa2 is to observe the activities close to small celestial bodies, but coming back to Japan. So it's a return exploration between the Earth and asteroid. So that is our final goal. So in parallel to the touchdown today, toward the end of 2020, for the return to the Earth, we are going to coordinate with other relevant bodies and organizations, and we are making preparations for that. And so ISAS is working toward the completion of the exploration of the asteroid, and so we'd like to seek understanding for our future activities and plans, and I'd like to ask for your cooperation in the future as well. So today we are resolved to make this second touchdown a success, and we'll be striving for that. So I'd like to ask for your cooperation. Thank you very much. Good morning, ladies and gentlemen. Hayabusa2 pinpoint touchdown operation live broadcast will be now starting. So 3.5 hours will be the program today as a live program. I hope you enjoy the program. So Hayabusa2 pinpoint touchdown live broadcast will be covered by the following guests. The operation supervisor, Mr. Satoshi Hosoda. I'm Hosoda. I'm a supervisor. Nice to meet you. Next is a system impactor responsible person, Mr. Hiroshi Imamura. I'm named Imamura. I'm responsible for the impacting devices. Ion engine responsible person, Mr. Ryuzaki Tsukizaki. Ion thrust engineer. So I'd like to broadcast to you from the control room. I'm a science communicator, Yuko Okayama. I'll be serving as MC. So there's one more person who will be serving as MC today, Mr. Okawa, who is in the exchange center. Mr. Okawa, can you hear us? Good morning. So those of you who are watching the live broadcasting, good morning. As former PR person at the ISAS. The weather is cloudy in Sagamihara City in Kanagawa Prefecture today. I am in the premises where the control room is located. And when the exchange center, there's a press center that is temporarily set up today. So since early this morning, a large number of media personnel are visiting here. So the media personnel have been reporting. As you can see in my back, there are broadcasting cars. Hayabusa2 News. You may have been you are going to watch the broadcasting on TV, and this coverage is being done. And from 11 o'clock, from 2 o'clock in the afternoon, the press conference will be held as well at the Exchange Center. It is temporarily not open to the public, but usually you can see the exhibitions in the centers as well. The summer vacations coming along, so Hayabusa2 exhibitions will be increasing in number. And the center is prepared for the summer vacation season as well. Across the street, there is a Sagamihara Municipal Museum, where public viewing is also taking place as well today. Then, we'll be showing the images. You can see the images inside the center, I wonder. Well, so this concludes my side of the reporting by the Exchange Center. Thank you, Mr. Okawa. Mr. Okawa will be joining us in the studio later. So basically, Hayabusa2 pinpoint touchdown operation control room. Special studio will be our place where we are reporting to you. As Mr. Okawa mentioned, Sagamihara Municipal Museum also has a public viewing as well. In Sapporo as well, in the Meteorological Society has also public viewing as well. So those people who are in the Sapporo, can you hear us? I'm afraid we cannot hear them. Anyway, please enjoy watching them. And those members who are joining the meeting of the Meteorological Society, please look forward to watching the broadcasting. SNS is also being used, and we are receiving your messages as well as questions as well. Hashtag Haya2_PPTD, pinpoint touchdown. And so that hashtag can be used. The questions can be sent to hashtag Haya2_QA. So for those messages and questions will be introduced while we are broadcasting to you. Other than those support messages, if you have any other messages, you can use the hashtag Haya2 to be shared among the people. Live broadcasting has the subtitle services as well. And so under this screen, you can see there's some subtitle over here. So this live subtitle can be a service for those people who are hearing impaired. And Ms. Akiko Hasegawa, who has a hearing impairment, also made that proposal, and thanks to the cooperation with the other people, we were able to make this possible. This is a message from Ms. Hasegawa, Hayabusa. So that's how you want to give it a try. And so that's the message of the Professor Kawaguchi, former project manager, after the returning of the first spacecraft. And so that made us very much passionate about this project. This is a very unique and interesting. So I got very excited by looking at the subtitle previously. So now this time, this is the second touchdown broadcasting, which will come with the subtitles as well. And so those people who are working all across Japan, the children, the elderly people, all the people in Japan, please enjoy this particular moment. That's very good to hear, because I'm very glad that Ms. Hasegawa watched the broadcasting, so that was very good as well. Then spacecraft operation will be the next one. What about the current progress? What's the current status? So the descending sequence decision will be made, which is gate 3 check. Gate 3 check was done, and now go sign was given. So the control room is now making preparations for the operations for the touchdown. There is some tense atmosphere inside the control room, and they are watching monitors. All of them are standing up. Almost all of them are standing up. Myself, Mr. Tsukizaki, is in the operation. I was my supervisor, and he was responsible overseas matters. And so we start calmly, but once we come to the critical moment, they look very tense. We're using the Japanese antennas right now. When something happens, then NASA antenna is also used as a backup. NASA's responsible people are also very much excited as well. I was able to understand their tense atmosphere over there over the phone. Now, so the whole world is watching this exploration then. Mr. Tsukizaki, he is going to report the operation from the control room. So I'll leave right at this point. So I'll talk to you later. Thank you. So, Mr. Okawa, and from the project side, Mr. Kikuchi is now present here. In place of Tsukizaki-san, Kikuchi-san is now, Mr. Kikuchi is present here now. So, good morning. Could you introduce yourself briefly? I am responsible for the selection of the candidate points for the touchdown. My name is Kikuchi. Nice to meet you. So landing site selection is a very difficult one. Sounds difficult, but where the spacecraft should be landed, that's what Mr. Kikuchi thought about. That's right. We'll be showing the slides to explain to the audience how we decided on the candidate points or the landing point. Then, with regard to today's operation, before asking about that, we'd like to review the past operations. So why don't we explain all that then? Could you show the slides? So this is the Hayabusa2 mission's outline. 2014, it was launched from Tadegashima and Earth swing by. And last year, almost 1 year ago, it arrived in Ryugu, and then a small-sized robot was landed, and 22nd, the first touchdown was done, and on April 5th, the impactor was also used, and so we are going to come to close to the touchdown at the near or crater area to collect super subsurface material. This is your expertise, Mr. Kikuchi. How did you decide the touchdown point? Could you explain that? This particular one is the altitude graph, isn't it? What's shown over here, as was explained earlier, Ryugu. From Ryugu, from the entire areas, we look at the entire areas and then narrow down to the particular point. As shown on the right-hand side, Ryugu geographical model, the three-dimensional model is used. That is put in on data, and we can show it on the computer. So we use that shape model. Then, where are bumps? And what are the angle of the slope? And those things can be mechanically calculated by looking at that. And so the place where there is no bumps or there is no sharp slope, we are going to identify those places. And then in the actual Ryugu, the safety was actually evaluated over here. The blue portion is generally safe places, right? The redder the color, then it's more dangerous. The gray is not allowed area, no go zone. So the equator is the area where landing will be possible. That's right. So this concept is put down in here. Plus or minus 30 degrees from the equator. So that is where landable place. The Earth and Hayabusa are communicating with each other, and we need to see the movement of the Hayabusa. As shown over here, Hayabusa2, when Hayabusa2 lands, and the antenna is shown to the Earth, and then between the Earth and the Ryugu, this line will be used to descend. And so when you go to the North Pole, the South Pole, and then the trajectory need to be changed. And then that will be very difficult landing. So about plus or minus 30 degrees from the equator. So that is the touchdown area. So this is put it in writing. This is the first time landing. So this is more of a little bit lax conditions, or is it more stringent? Particularly the second one, say diameter 100 meters, flat area, it says. spacecraft accuracy is about 50 meters. We took that into account. Along with that, we considered to find the about 100 meter flat area. But once you go over there, there are rocks only. And so considering that, we, particularly the second one, the landing accuracy has been enhanced. In that way, we made a plan.
Now, this is TD1 of Hayabusa2, and we selected 2 point. One is larger, the other is smaller. Ultimately, we chose number one area, smaller one that we have chosen, E1, because a blue area is free from many rocks, and therefore it is safe to touch down. And therefore, we have prepared this kinds of chart, and project members have continuously conducted discussion, and we finally chose the green areas. So it maybe sounds simple, however, it took a massive amount of time to decide. For example, this is data derived from the Nagoya University. This is the public release, where the yellow, pink, red, all these are rocks. And in that, the red is quite dangerous for our SEI. And also, yellows are also risky, high risks. So we have selected the area, and only a very limited area are selected for the safe area for the touchdown. The science team, the big camera team, and also geometry teams have selected, and all these works are manual work where they have to count the number of rocks. So we prepare this type of charts, and we have selected the safe area for landing. And when we look at this area, the area without any pink or red rocks, and we already have narrowed down. The 3 meters in diameter is the area where we were able to land. So this is the guidance system, very accurate in the case of the Mars, and it will be 1 kilometers in diameter. So compared to that, our accuracy is very high. Of course, there are gravity and atmospheric power pressures and so forth, so all the conditions are different from the Mars. However, qualitatively, this is quite different from the landing on the Mars. So that's the nature of this particular project. So we have to achieve the accuracy of meters, and the centimeters level of margin of error need to be eliminated from this project. So when you hear the actual operation, we will probably be able to explain later. However, it is not an optical work, but this is the co-working with scientists to identify the location safe for the touchdown. So that's the critical point. Yes, that is correct. As is mentioned earlier, we need to count the rock one by one. We need to create the exact geometric model on the landing area. So the science team and engineering team are working together side by side to be able to select the particular touchdown point. And thanks to Kikuchi-san's hard work in the previous touchdown point, this is the camera at the bottom. Are you able to pull out the visuals? Right on the spot, yes. In the previous touchdown, this is the Sanzu Iwa, which is a big rock. We were able to avoid that big rock, and we were able to make a touchdown. And then there are so many rocks and sands flowing around in this area. We were able to confirm that visual. I am awed by this graphics, and we should see the similar one this time as well. Now, could you explain about SCI? Now, this is the SCI, small carrier impactor. Let's go to this particular topic. So this is the finish of SCI, and by activating the SCI, there is the copper worth about 2 kilograms are crashed into the surface of the asteroid at the 2 centimeters per minute. So on right hand side, right after the separation, the camera started to take the picture, so we were able to show this photo taken on the 5th of April. And there are explosives. An explosive part is shaped like this, and this is the model of a scale of 1 to 10th. And actually, this is the diameter of 30 kilometers, and there are explosive inside. And the top part is covered by the copper, and this part will be expanded like a bloom, and because copper is very expandable, and therefore it will blast like this. So this is the picture from the testing on the ground. Should I play the video? Yes, this is the video on the testing of the explosives. I've played this in April as well. So this is a big scale explosion that was conducted on the 5th of April to Ryugu. And here is the operation at the time of SCI testing. Now, as Kikuchi-san and Hosoda-san mentioned earlier, from the Earth, it always has to approach toward the Ryugu, and we separated the impactor, and after that, it will go behind the Ryugu. So that is the sort of escape operation. After that, SCI was operated, and on the surface of Ryugu, there was a crater made. May I? And exactly on that particular point, we would like to land touchdown. Shimamura-san, excuse me. This is the control room, control center. We are in control center. This is at Tsukizaki. Now, Doppler pointer, which will detect the situation of the explorer. We received that image, and we were able to check the delta V after the hovering. So in the sequence of touchdown, it is number 0. So if you switch to 0.0 of the chart, so it's 0, which we were able to finish 0, and moving on to number 1. So switching to number 1 again. So altitude of 30 meters. We are maintaining that particular altitude, and we have started a hovering at this point, and we were able to confirm the start of the hovering. Thank you very much. We are approaching as we speak, and please report and update later. Thank you. Well, we need to quickly go through our topic as well. Now, at the time of separation, this is the SCI. This is a TIR measuring the temperature, which is showing this image. And also, the separation camera is installed as well. On left-hand side, this is the camera area which this particular part is separated so that activation point in time is captured as well. So 14 seconds after and the 3 seconds after the separation is measured, and at the 3 seconds later, ejector curtain is been photographed. Left hand side you will not see, and right hand side you will see the curtain. So this is the 14 seconds prior to SCI and also 3 seconds after SCI. So I will ask that particular topic later to scientists. After that, this is the exploration operation, and all these points were circled in yellow, and S01 red is where the SCI was activated. And the area where a crater was being produced, and right in the middle of this crater, there is a point of impact. So that was the charge. So this is a fantastic operation that you were able to achieve. And after that, we have taken several photos. On left-hand side, this is the prior to the impact, and right in the middle is the time of the impact, and right-hand side is a blink image, we call. And right in the middle, the rock is moved clearly. You were able to see that the rock was moved, and there were big rock. As a result of that, ejector direction was only a part of the directions, not all across, and therefore separation camera was only able to take a part of the photo as a result of that. Well, let's cover that topic later, and let's talk about today's touchdown operation. This time around, the area where which we landed last time was here, red point. However, a quarter rotation was made, and here is right next to the crater where we made a crater based on SCI, and the blue point is the target of our landing this time. Switching to the PC today, Kikuchi-san. This is the photo taken out of the camera. So TM is target marker. use target marker as our target, and the operation is to target at this target marker and changing and coordinating the altitude. There were several rocks, however, a target marker is exactly the area which we would like to target at. So we were able to launch the target at the exact point that we would like to target at. So this is a safety evaluation chart where we are able to land on a slightly wider area. Previously it was 3 meters and this time it is 3.5 meters in diameter. It is still a challenging situation. However, we were able to select the area where there is no rock in this particular area. This is the explosions and materials from the craters, and we are trying to land on the area where the crater emitter will be observed, and we will ask that question later to the professionals. We have started a touchdown operation already, and we already finished number 1. We are hovering at the altitude of 30 meters, and we are trying to find the target marker. So we will be explaining later by doing the operation. We will be going down to the altitude of 8.5 meters, and we will target at the final touchdown, and probably slightly after 10 or perhaps at 20 minutes past 10 is the earliest time that we were able to make the touchdown. This is the control room. We will soon change from hovering to, well, there are Dopplers and telemetry. Both are used, and telemetry will be discontinued. And after that, the controller room is paying attention to the Dopplers only. And we are carefully monitoring, and there will be a major event very soon. So the very final phase is ongoing as we speak, and we are waiting for the target markers to be captured at any moment. So please pay attention to the Dopplers. Maybe, well, there are some noise in the control room, so Doppler has been checked. We will read the situation. Well, could you explain the differences between Doppler and telemetry? Telemetry is captured from satellites and the signal emitted from the satellites, and the Dopplers are the Doppler effects, right? And there are the electric wave emitted, and the changes in the frequency is measured to measure the movements of Hayabusa2, whether it is moving forward or backward. This is control room once again. Exactly now, the target marker capturing is being evaluated, where the Doppler frequency change is now being evaluated, so that we are checking whether the target marker is being officially captured or not. Because if we fail to catch the target marker, and we will not be able to move on to the sequences of operation today. Now, the telemetry data will not be used because antenna will not be directed towards the Earth anymore. So the Hayabusa2 will take the attitude that the touchdown operation should be made on the Hayabusa on the Ryugu asteroid, and therefore we will only rely on the Doppler, and therefore we are carefully monitoring the Doppler monitor and target marker capturing. We were able to see the sequence of changes in frequency that is very likely that we were able to capture the target marker. So sequencing 2 is the operation which we are in. We are in sequencing 2. So far we've been hovering at the altitude of 30 meters. However, since then we are gradually descending the altitude. So our explorer is moving toward the surface of the Ryugu. Back to the studio. Thank you very much. Thank you. Now, we will be speaking out of the smaller screen now. Exactly now, the video graphics are prepared, and we have computer graphics to prepare for explanation. Kikuchi-san produced this particular chart. So I will be talking with Kikuchi-san, and I will explain the movements using the smaller scale model. Like Tsukizaki-san mentioned earlier, basically, can you see this? Explorer is, first of all, is showing its antennas directed to the Earth. And the landing point is, this is a northern part, where this is exactly the blue dot, where in order to land, we need to change the attitude of Hayabusa2, which needs to be very parallel to the ground. And with that reason, that antenna will be away from the direction toward the Earth, which means that we will no longer be able to use the fast speed communication. And that's why Dopplers are used, where we were able to visually see the speed. Using the Doppler wave, we can detect whether the Hayabusa2 is descending or ascending. Right. Doppler waves are the only ways to be able to catch the movement of Hayabusa2. Now, the next step will be that once it captures the target marker, descent will continue at the altitude of 8.5 meters. So once the target marker was captured, and then, as is mentioned earlier, the attitude will be changed, angle will be changed in order not to crash into the Earth. And after that, during this time, the target marker will be right in the center of the camera. And in that way, the Hayabusa2 will be moving, and our final target several meters away. Therefore, it will be a slight shift horizontally, and then we will landing straightforwardly to the ground.
And the tail up. So ion ending will be increased in order to prevent a collision. So if we look at the situation from the side, the sampler horn is this, and this once touches the ground, the tail will actually come down. So in order to prevent that, we will descend horizontally to prevent the tail from colliding to the ground at the impact. So it will come down with the tail pointing up a little bit. Kikuchi-san probably have to go to the control room, so we will continue with the explanation. Thank you very much, Kikuchi-san. All the best. So Okawa-san is now back to take the place of Kikuchi-san. So Kikuchi-san, thank you very much. And Oka-san, welcome back. And let's explain together. Now I'm back. And the capturing of the target marker, and there is a camera on the bottom surface of the spacecraft. It's called ONC11, and so this camera will capture the target marker. Yes, there is a spacecraft mode, and as you have indicated, and there is a camera on the bottom, the surface of the spacecraft, and we'll do a control to have the target marker directly underneath. That is considered to be the capture of the target marker. But the cameras and the laser is somewhat not clean because of the dust that has come up at the first touchdown. And so we have increased the light, the receiving sensitivity of the camera in order to respond to this situation. But there are some the anxieties. We are in the control room, and we have been able to confirm change using Doppler. So far, everything is going as per scheduled. And we have been able to confirm the situation as we have expected. We started hovering at the altitude of 35 meters, and we have descended to less than 70 meters. We will continue the descent. And like Kikuchi-san has explained, when we reach an altitude of 8.5 meters, then we will change the attitude of the spacecraft, making ready for the touchdown. And we will inform you when that moment has arrived. But we are still in the second part of the sequence. But you can keep the camera on the mission, the control room. the length of the sampler horn is about the same height as the rock nearby, because you said that you need to raise the tail. Yes, if you actually raise the tail up a little bit on the descent, it's more safer. During the SCI operation, Morrison was responsible for creating the artificial the crater. And because of the impact being discharged, the height has been increased, so it's a little bit easier in terms of operation at this time. And the center of gravity, and if the sampler horn was located there, then we won't lose the balance. Oh, the studio. If you could bring up the number 3 of the touchdown sequence. And the spacecraft has arrived at the altitude of about 8.5 meters. So situation-wise, we have been able to confirm at the control room the situation of Doppler at the altitude of 8.5 meters. Looks like the staff is looking a little bit relieved. And in the middle of the control room, you can see the project members, and they are smiling a little bit. But still the same. We are only above the target marker. So if we actually lose the center of the target marker, the spacecraft will abort the sequence, and so there are still a level of nervousness. I think we are starting to change the altitude towards the touchdown. In other words, we are raising the tail. And I think that's the kind of situation. So we've raised the tail. And so radar to LIF, yes, and the handover have been confirmed. So LRF is used. Laser rangefinder is now used instead of radar. This is more a closer distance, the altitude meter that we are using. And the altitude is now down to 8.5 meters. And we are shifting the attitude, towards the touchdown. And so we are making pretty good progress in comparison to the expected the progress. So if everything goes as steadily, then we will start the final descent next. And so the spacecraft will be ready for the touchdown, and will go down vertically towards the landing point. And certainly a nerve-wracking moment. So until 8.5 meters, you have descended by having the target marker in the middle. Then you will actually look at the target marker from a little bit of the side, so changing to the touchdown location. Then after that, we will just go down on a free fall. But looking at things, by using only Doppler, it's not that easy. But the operation team had done a lot of considerations and looked at things in details, and to be able to understand the situation by just looking at the signals. The touchdown on the first occasion was something that occurred in a very short space of time. It was just at an instance. Now, from the control room to the studio, and the horizontal motion, number 3 in the touchdown sequence, an announcement was made that this was done successfully. So the attitude, the team has reported that the horizontal motion has been done successfully. Then 5 or 6 minutes from now, we're going into the fourth part of the touchdown sequence, which is to make the final descent. So we will be moving to that sequence in a few minutes' time. So please maintain this screenshot so you can see the control room, and towards the right, towards the right top, you can see the touchdown sequence. And the studio, we only have a few more minutes to go before the touchdown. But still, the situation of nervousness continues. If the spacecraft decides that it is in danger, then it will abort the touchdown operation. So it needs to be safe before anything else. And after pursuing safe, we will obtain what we want to obtain. And for that purpose, we have made preparation as much as we can. And the spacecraft will change to the final descent sequence. Now, Hayabusa2 itself, using its functionality, making judgment as to whether it is safe or not. Yes, that's right. There are various items, but say, for example, one, to be able to achieve certain things within the given time, like attitude and also attitude. If the altitude is different to what was scheduled, then it will make an emergency ascend. LRF, to understand the altitude, is the laser range finder. We're using 4 beams to understand the altitude, and also looking at the target mark at the same time. And the target mark, I think, is including the names of 180,000 people. My name is there too, so is mine. So from the surface of the asteroid, I hope that the target marker will invite the spacecraft down. And the final part is going to be free descent. And when it's hovering, if we don't do anything, then the gravity will cause the spacecraft to come down. So we are using the thruster to point upwards and then come down. Then thruster is used to raise a little bit to counter the gravity. But in the end, we want to use the proportion. It will just come down. So free descent. On the horizontal axis is the chronological progression. Well, because we are going to raise the tail, so tail up, and so we'll more or less come straight down. So it's not the case that we will come down horizontally. We're looking at the chronological progression on the x-axis, so the spacecraft will just come down straight. That's what this the graph is showing, because this graph is showing the chronological sequence. And it is tilted because the tail is raised, and the attitude is not the level, so it's kind of tilted. So from the surface of the Ryugu asteroid, it's the tail is raised a little bit, and Ryugu is making is actually rotating itself, and so we need to track that. And once we start the final descent, I'm sure the expressions on the faces of the staff in the control room will change a lot. And on this occasion, the camera is a little bit clouded because of the dust that raised during the first touchdown. This was assumed that in the second touchdown. Did you know that the light receiving volume will be lower? Yes, we can increase the sensitivity. And the previous occasion, the hovering descent, the altitude was 45 meters, but this time 30 meters. So we felt that we'll be able to do the descent operation on this occasion at a risk level that is equivalent to lower than the previous occasion. So even when the camera is a little bit underclouded, we came up with sequence to make sure that that will not become disadvantageous. But we had the SCI, the impact, the released, and then there is a little bit of impact, and the impact of the separation will remove some of the dust that has stuck to the camera. This is the Shikizaki from the control room. Then the Doppler monitor showed a significant change. And we are now in the number 4 of the touchdown sequence. Yes, you can see. You can just bring up that the sequence on top right. So, and the count up has started at the control room, and we are now during the final descent to the asteroid. If it rises too much, then it's a miss detection. 50 seconds. Should be soon. Should be very soon. If everything goes well, 90 seconds is the time for touchdown. 20 more seconds or so. Please come down. Please go down to the surface, Hayabusa.
拍手が起きてます。
Yes.
拍手が起きてますね。
There's a big round of applause in the control room. Let me clap as well. The touchdown sequence. Please go to number 5 of the touchdown sequence. So we still don't know. And we were able to see the velocity of rising. It wasn't an abort. It wasn't an abort. It was a normal touchdown Doppler screen that we have been able to confirm. So we will now enter into detailed confirmation work. We haven't made a final or official success judgment as yet, but we have been able to confirm everything that we had predicted, so people look quite relieved. And you can see all the team members shaking hands and also the having a hug. So what needs to be analyzed to certify that we have made the touchdown? So we need to point the antenna towards the Earth and return the telemetry. And at that point in time, we'll be able to confirm to see whether all the equipment has been in order. Then we'll be able to confirm that the touchdown.
Up until then, we cannot make a judgment whether that has been successful ultimately. But as long as we see the control room within certain time range at the proper velocity, it is running smoothly, and I'm very much looking forward to the report from there. Doppler, and looking from the Earth, the Hayabusa2's movement, direction, and velocity were captured, and within the time arranged, it is moving to the Earth. It is going away from Ryugu. That was confirmed by them. That's why I believe that they were clapping hands. Then, as if everything goes smoothly, in 20 minutes, the communications with the Hayabusa2 will be recovered. But up until then, we still have time. We have the second guest. Hayabusa2, the analytic science is his expertise. A professor of Hiroshima, Professor Yabuta, is now in the studio. Nice to meet you. So could you introduce yourself first? I'm with Hiroshima University. I'm Hikari Yabuta. Hayabusa2. In this, I was involved in sample analysis. Organic matters are analyzed, and I'm one of the supervisors in that team to put the studies together. What about the scientific purpose and the significance of Hayabusa2 then? Shown on this slide. Let me use this slide then. Hayabusa2, as you know, has organic matters and water. It's carbonic. The materials were captured and then bring back to the Earth and analyzed, which is a sample return mission. And then the solar system and life origins and how the evolution has taken place, as well as identifying the history formation of asteroid. And in the Ringu was focused upon over the last 1 year. We have come up with some results from the 1 year observation. That is, the surface is very black. That's the most black planet in the solar system. That's one characteristic. That means it's much more black than any stones available on the Earth. In the solar system, in the planets in the solar system, that is the most black color. And it's like an abacus shape on the equator. The radius is 450 meters. And on the surface, there are many boulders and rocks. And so it will be very difficult to land, and find a landing spot was very difficult. And the density is very low. And those are the characteristics. And organic matters and water are contained. And Hayabusa2 tried to capture those materials. Now the people in the control room are clapping hands very much right now. So they're clapping hands from the control room. Tsukizaki-san, why were they clapping hands? So far everything is running smoothly. And that's why they were clapping hands. As I mentioned earlier, in 14 minutes or so, then telemetry will be coming back, and so whether that was successful or not will be judged finally. But so far, everything appears to be very smooth and going smoothly as scheduled. So we feel the very strong enthusiasm and excitement from the control room. In Hayabusa1 and Itokawa of celestial body, asteroid, there were hardly any organic matters or water. In Hayabusa2, for the first time in the world, organic matters and water were explored by Hayabusa2. Why organic matters and water are very important in the asteroid is because, as shown on the right-hand side, organic matters are comprised of elements, and the oxygen, nitrogen, those are those elements are the most contained in the solar system. Those are the elements, the raw materials in comprising the solar system. And particularly in the dust before the solar system was developed, ice, organic matters, and mines-based dust, those are existing. So that is a verified from various observations. And then the molecules, clouds, have been separated into small ones, and in that process the chemical reaction was taken place, and the dust was contained, and which now turns to a small asteroid, and then asteroids and other Mercury, those things will be made, comets will be made, and which comes down to the Earth is called meteorites. And after the Earth was made, the Earth comprises water and organic matters that are originating from those asteroids and comets. And so the identifying the elements of a small celestial body is synonymous with identifying the origins of the Earth. And so there may be some common features with the asteroid, or the common things between the Earth and asteroid. And so that seems to be very much of a big difference in terms of scale, which is asteroid 300 million kilometers away. And so as one of the major features is remote sensing observation and small-sized landing, which is called Mascot and Minerva. there are two landers and the sample analysis. All these things are all combined from the large scale to a small scale. That means from kilometer scale to a nanoscale. We analyze the Ryugu from a wide range. In that way, you can identify what constitutes Ryugu. Then the subsurface materials are to be captured, and touchdown appears to be very much successful. Well, we don't know yet, but looks like it. And people are very much excited. Subsurface materials, the scientific value of subsurface materials is, if I quote, this is a quotation from the reporter briefing materials. When you compare the subsurface materials, and then the heating from the sun and the metamorphosis taking place on the surface can be identified. And if the subsurface material is not modified so much because of those elements, and then as compared to the surface sample, more fresh initial solar system period records can be identified. Particularly for the organic compounds are say dissolved by the heat and carbonized, and therefore by looking at the subsurface materials, the initial solar system can be identified, and the asteroid surface a mixture of the materials can be identified. You can also tell how old the materials are. So the February touchdown and the touchdown at this time samples can be compared. In that way, the heterogeneity, regional heterogeneity can be identified, and we can conduct a sampling multiple times. And that is for the first time that there's Hayabusa2 has conducted that particular technology can be established with a high reliability. I think that can be said. Now, from the internet, there's a question. Mausi-san on the Twitter as well, on the touchdown at this time, the samples that are supposed to be captured, the surface one and the subsurface one, how do you say differentiate those two materials? Mainly, with regard to this one, we analyze gas. So there's a team that analyzes gas, and they have a very firm indicators. For example, the sun originated helium-3, and so isotope can be used. And then on the surface, surface and subsurface, how that the radiation from the sun is applied, you can make some relative comparison in between. There's one more question, Koike-san. Now, in order to execute this touchdown within the operation team, I understand the opinions are two opinions, whether to have a second touchdown or not. But so that means you went ahead and decided to have the second touchdown. That means that there are more samples that are more attractive can be obtained. Well, when with this touchdown, we can make a comparison between the first touchdown samples and the samples from this time, because the surface materials are very attractive as well. By comparing that with subsurface materials, we can see how much metamorphosis is taking place or denaturation is taking place, and so we would like to make comparison between the first touchdown materials and the this time material samples. There's one more question, Ki-san. How do you analyze the samples? Photomatography will be used or not? Chromatography is used or not? We have an initial analysis team. It's an international team comprising 200 members, and it is divided into 6 sub-teams. One is the element and isotope elements are analyzed, and from the minerals, quite a large particles are analyzed, and super small particles are also analyzed by some other team. Also, molecules are also analyzed depending upon their size by several different teams, and there's a gas analyzing teams as well. We have many different sub-teams as well. So depending upon each of those sub-teams, the analysis methods can be applied in a various way. So organic measurement technology and inorganic matter, organic measurement, the tools will be different. Microscope can be used, or the material can be melted and then separate them. Such a method can be used as well. So there are many different kinds of methodologies and methods. We are discussing the strategy for analysis right now. Now, for artificial craters, a picture is captured in here, which is now shown over here. Now, you are focusing upon the C01 as a touchdown. The dark portion is visible over here. The color, this coloration takes place. Is that because of subsurface materials are there? Subsurface materials or SEI was used for collision testing, and because of that collision, the materials may have underwent metamorphosis, and both of those materials may have been exposed to the surface. That's our speculation. So there is a significance of making comparison, and you mentioned earlier that makes sense. You explained that, and that explains it. The meteorites are already available on the Earth, but there are things that we cannot tell from the meteorites, and that can be identified by capturing the samples from Ryugu. And what will be different, and what can you expect to be different from the samples from Ryugu? In terms of, in case of meteorites, from the asteroids, those are flying to the Earth. That you can expect in that way. But from which asteroids and or the small celestial bodies? What is the geology of a small celestial body? Is it from the subsurface or from the surface? We don't have that data. We don't have that information when it comes to meteorites. And so through this exploration, the composition and topographical information can be linked in that way. In that way, we can identify, elucidate the history of our solar system further. Once those materials are dropped to the Earth, and then not necessarily those not the materials from outer space are not freshly available on the Earth, because they may be polluted from the Earth materials.
Well, not everything that I'm mentioning about. However, part of the meteorite may be affected by weathering, be it rain or maybe the oxygen on the Earth. And of course, the surface of the meteorites are completely burned out, and the inside is less susceptible to the thermal changes. However, of course, the sample of meteorites could be lost because of the surface exposure, and therefore, through this sample return operation, we will be able to elucidate on that. And you have directly coming from the International Congress of the Space Exploration. And at the level of Congress, what is the major topic at this point regarding this topic? Well, return sample analysis are drawing a lot of interest. Many experts are gathering together. Day one of the Congress, we were able to host the special sessions for the Hayabusa2. We were able to present and share many information. We had a lot of excitement. And also on the first day, we have the kickoff meeting for all the relevant researchers and the RSub session committee as well. So the full week was full of excitement. And thank you very much for coming from the Congress right away. Now, Doctor, you will be going back to the control room because telemetry data will be returned to the operation room, and therefore, please go back and continue to work. Thank you very much for spending time with us. Earlier, during the live broadcasting, Dr. Kikuchi was full of a smile and clapping hands, and I heard a lot from him about the hardships of this project. So I feel this is as if my own children is succeeding in something. And probably if we were in the control room, and there will be so much excitement, I am willing to go back to the control room so that I will be able to see firsthand the antenna data. Kikuchi-san, because of the time constraint, wouldn't be able to explain quite well. Monte Carlo simulation was made many times, like hundreds of thousands of cases that he simulated and made sure about that there will be no collision vis-a-vis the rocks, and he made sure of that. So therefore, the safety margin is 1 out of 100,000, I would say. And as Dr. Yamamoto mentioned, this is quite highly valued from a scientific point of view. First, the landing the target marker was quite good. This is Tsukizaki of the control room. Antenna came back to the direction of the Earth, and we were able to check the telemetry data. So far, there's no problem in the data. Big round of applause happening in the control room. We will be checking the data. We did the single round of a check, and it was a green sign. Green sign means everything was okay. So I'm looking forward to see what Tsuda-san's going to mention. And there are low gain antennas to high gain antenna, where the telecom is now being replaced, and that was successfully replaced at this moment. And Hayabusa smoothly changing the direction to look toward the Earth. And there are 2 major antennas installed on the top of the Hayabusa, and everybody was raising hands and clapping hands above the heads. We have yet completed all of the gate checks to declare the success or the failure of the operation, and yet we already had a big round of applause, and we are still working to finalize the checking work. This is a great challenge and difficult challenge, and this is great to be able to share this moment. So we are very much moved and overwhelmed. Well, this is Hosoda. I will be going back to the control room. Good luck. So gate check was mentioned several times, and does that mean that whether you are clearing the checkpoints for all possible steps? Yes, there are several gates been set in our course, and we check certain items designated for each gate, and all the person responsible will be checking the area which they are responsible for, and they will show the OK signs when everything goes well. So like Dr. Tsukizaki mentioned earlier, this is a green sign, so everything is green, and we will say that as all green, and the project manager, Dr. Tsuda, will declare that we are ready to move on to the next gate. So that's how the operation is organized. So far, as Dr. Okawa mentioned earlier, low-gain antennas were installed surrounding the Hayabusa2, and that is a highly high orientation, which means that whatever direction, the antenna will be able to communicate. So even if Hayabusa is not directed toward the Earth, and low-gain antenna will be able to send the signal. However, the quantity of information isn't quite high. So it is a level of the Doppler, and therefore we were able to detect the attitude of Hayabusa. However, in regard to sending many signals, we need high gain antenna, and therefore the Z face would have to be directed toward the Earth, so that we have high gain situation is going to be achieved through antenna. And the high gain antenna could be communicated with the limited scope of the directions. However, it allows a lot of information to be transmitted, and therefore now high gain antennas are directed toward the Earth, and therefore the high quantity of data is been available for transmission. Do we have the camera screenshots in a sequential way? Can we expect that to receive? Yes, that is actually a high volume of data because it is a major information, and therefore we check first on the signal level whether the high gain antenna is on or off, or whether that we were able to eject the bullet or not. While doing so, of course, we are capturing the imagery pictures, and we are selecting the priorities to transmit the data back to Earth. So on the touchdown moment, the bullet was ejected, and therefore they started to capture the subsurface material. Yes, that sequence of operation is the same as the touchdown first. We had the Dr. Yamata earlier, and in the question earlier, there's a person, Macha-san, in the artificial crater. They are, of course, be able to obtain the samples which are not influenced, exposed to the space weathering. However, why are you landing on the surroundings of the crater? Although there are some dark color area, but you are not landing on the center of the crater. Yes, if you could go back to the personal computers, be appreciated. Well, not available. However, it is true that we were able to land slightly outside of the crater. The reason is to secure the safety. That is the first reason. If we are in the crater area where we've shown you a blink photo before and after the crater impact, we were able to create a relatively good size and the depth of the crater. And inside the crater, because there are some depths, and therefore it is not even, therefore it is very risky. So Hayabusa is having the panel on both sides, and if the impact was too deep, and then the puddle or maybe touching on the crater and damaging the puddle, and that is a great risk, and therefore think about such risks. We selected a location where it is close enough to the crater where we were able to get the samples inside the crater. However, there is no major rocks or major unevenness on the surface. So that was the work conducted by the teams. We were able to select the best position to take sample and be safe. The first starting point of success, of course, is successful ejection of a target marker. But it seems that sense of relief may be spread around the control room. But we are waiting for the final call for success. And ultimate decision will be officially announced at the press conference at 2 o'clock this afternoon. This is Tsukizaki in a control room. Now, the data from Explorer is now received in this room, and we started a computation work to make judgment of success. I'm not sure how long would it take to finish this computation, but soon enough we will be able to make an official announcement whether the operation was success or not. Each and everyone is checking the data on their computer and terminals, and they are checking the data whether the touchdown was successfully done or not. They are making a thorough analysis in order to evaluate the success of this operation. Earlier, you've shown the red high gain antenna. Now all teams have responded and they integrated analysis in beam. So what kinds of teams are you there? Well, attitude, sampler, and observation equipment, and attitude control systems. Well, there has been no problems being reported from each team. In the control room, there is a screen in the middle, And attack 25 panel as we speak, there is a light green area. For all of the slots, we would expect to have green signs, and if all the slots are lightened by green, then that's a overall success. We now would like to invite the next guest speaker at this juncture. Now, I will return back to the studio, and here's another special guest. Please. Right, then we will invite two special guests. Excuse me, this is control room to studio. This is exactly at this moment. Big round of applause here in this control room. All the items were confirmed as success. TD2 is a success. Look toward this camera. Let's make a V sign. Here we go. Touchdown 2 was a success. I'm so happy doing this job. Thank you very much. Thank you very much, Tsukizaki-san. We were able to hear the great excitement. Let me then introduce the guests. Project scientist for the first Hayabusa, and he is the professor of ISAS, Dr. Akira Fujiwara. Very nice to meet you. Another guest speaker from NEC. He has involved in the Hayabusa #1, and he's in charge of the space PR activities, and also he's in charge of the recruiting for the space business, Mr. Ogasawara. Now, we were able to hear the round of applause at this moment in time. What is your feel at this moment?
Dr. Fujiwara, everything has progressed quite smoothly, and I'm very happy. In particular, at the Hayabusa 1, the sampler didn't function properly. So in reflection of that, it's been several decades that we have achieved a success here. So I'm very happy. Dr. Ogasawara. And Dr. Fujiwara, you said several decades, but it's 14 years ago. It was only 14 years ago. and this type of live the broadcast, and I didn't think I was going to be sitting here, but perfect on this occasion. And during Hayabusa 1 there were many things that and was nervous all the way through, but I was very relaxed and relieved and to be here, and I'm very happy that I'm here. Dr. Fujiwara, let me ask you a number of questions. You said that you are very happy with the success of the sampler. Now, the touchdown on this occasion, and you wanted to obtain samples from the asteroid. And when you collect sand or stones on the surface of the ground, you use the shovels or hammers or things like that. But on this occasion, you've employed quite a unique methodology. So, Dr. Fujiwara, you have been involved from the ground design level of Hayabusa. So in terms of the sampling method employed on this occasion, what are some of the key features, and why did you choose to use this type of the approach? Maybe if you could reflect back. And as you know, asteroid is very small celestial body. And the gravity on the surface is almost nil. And if you try to dig using a shovel, you will experience rebound as a reaction. And together with a spacecraft, you could be thrown away from the surface. And so we needed to use some kind of a projectile, if you like. And shoot a projectile and catch what rises. Now, by chance, I was involved in the research of asteroids, and I was studying the evolution of an asteroid. Now, the collision process plays a very important role, and as part of the simulation, I was involved in looking at a collision with the asteroid. So this was on my mind, and I wanted to leverage that, and thought about developing a sampler from such a perspective. And maybe we can bring up the slide for the sampler. So initially, we came up with a very simple the structure, cone structure, which we were thinking of using to capture the samples. So the fire, the projectile from the side. So we started experiments like that, and initially. And we were thinking of a kind of the funnel, like which conical together with the projectile, and we felt that this would be quite high efficient in terms of collecting samples. But there were a lot of restrictions from the spacecraft side, and so we ended up with something different. I was very dissatisfied at that point in time. Then that was the first point. And second, after the shooting a projectile, what should we set as an ascending speed? And we had to have a discussion with the engineers, and we needed to rise relatively quickly, otherwise there will be damage to the spacecraft. And so we needed to ascend with the certain velocity. So there were these 2 points. And to be able to look at whether we can collect samples in large volume safely, and that remains to be the key. So until we return, I'm still worried as to how much samples that we have been able to collect. I really hope that the spacecraft will come back to Earth. I am back from the control room, and this is Hosoda speaking. And this is also something that we have been doing from the past. And this is a device for shooting a projectile at high speed. So there is an explosive the part, and the projectile is shot out. And we had a mock-up sample on the other side, and we did a test. The speed is several kilometers per second, and that's the kind of speed we can achieve. I was working with Dr. Fujiwara and Yano-san and Hasegawa-san. They were involved in the work with you. Then you were thinking of an Oscillix arm, but the doctor, you have come up with this type of megahorn all of a sudden and said, let's give this a try. And we did the experiment using your method, and we understood that we are likely to collect the sample. But thinking of creating something that doesn't deform. And in that respect, we want to be flexible. And we have discussed with the engineers and identified there was this type of possibility. So we decided, had it been metallic, they kind of the kind of flex and basically shoot up the pieces, and we felt that we can collect samples. But with regards to the sampler horn, what's the length? And what was the basis for determining the current length? And there was a relationship with the rocket and the spacecraft that had led to this length. These are photos from Hayabusa2 on top of the sampler horn. We have a gun for shooting the projectile. We did tests on the ground, and we also you had to do verification based on the small gravity as well. And within the container for the small gravity, we couldn't actually place this in an original size. So we had to actually scale down the size, and we came up with the calculation and method to see that this is likely to work. Now, the conical the matter or the device that we were using initially for consideration is on display at the museum section. So, Dr. Ogasawara, I'd like to ask you as well. I'm wearing this type of clothes. This was the project jumper for Hayabusa2. I was involved in Hayabusa2, so I was pondering what to wear today, but I thought this would be the best, so I wore it. It's been a while since I wore this, but I was kind of recalling back to what we were doing back then. Now, I was originally involved in the orbit calculations, and my first work was a Halley Comet, and that was back in 1985. Many of you may not have been born, but that's where I started. And we did a swing-by experiment using a Hiten satellite, then Kaguya, then Hayabusa. I've been involved in these. And today, I brought something, and this, do you know what this is? Normally, you don't see it in this shape, because on the surface there is a reflecting sheet, and so often you can't see what it looks like in the inside. Many of you probably have not seen it inside. When you actually tap it, and you know what it is, it's an aluminium cube, and this is the target marker. This is what it is inside the target marker that had enabled the Hayabusa2 to touch down today. Now, there were many things inside. There is a small particles inside. Why do we do that? Like Fujisawa sensei said, there is almost no gravity. So if we just drop something that is completely empty, it just continue to rebound up, and it won't stay stationary. And marker needs to stay stationary to the work its function, so it need to remain still. So this is what I thought. I am bringing things up like magic, and people are thinking what this is. Many of you don't know what this is. This is a kind of the kids' toy, the beanbag, game of beanbags, and it's useful. But when it actually collide with the ground, the little beans inside will just rebound up, and as a consequence, the target marker will not move very much from the land of position and will remain stationary. And this is kind of beacon to guide Hayabusa2 as close to the candidate landing point as possible. Now, so this is 250 billion the meters. So 1 in 100 billion. And the touchdown precision, so the 2 or 3 meters we may have been away from the target itself, but given the total distance, that's the kind of fraction you're looking at. So some people talk about shooting down a fly in the United States from here. No, we're not shooting a projectile to shoot something. We have many people in the operation room. These people guide the spacecraft, and when the communication from Earth will not reach in time, then the camera on the spacecraft will capture and chase this, and achieving this 1 in 100 billionth the precision. I've actually wrote this in meters, and there are so many zeros, and that's how far away we are. But some people say that we should write this in millimeters rather than a meter, but that means we'll have too many zeros. But one attractiveness of exploration is that we are doing this based on human mindset and thinking of new methods to bring back things. It's not something that can be done naturally. It's people who actually do the work to enable the sample return. And looking at the operation room or the control room, there are many young people. I am old, and I'm able to sit down here and be involved in a broadcast. Now, I can actually look on with a sense of security, because what we experienced in Hayabusa1 has been evolved and reflected into Hayabusa2 for its operations, so that the hardship, the difficulties that we encountered have been passed on to all these young people. People from the JAXA, the people from NEC, the manufacturer is the same. Some people who've been with us only for 3 years are part of this project. And I was introduced as having a position of recruiting. Now, the space exploration is such an exciting area. I want young people to participate. And you can join JAXA, you can join NEC. There are so many different opportunities for people to contribute. And this was a comment as a recruiter, I feel like. And Dr. Ogasawara, I understand there are people who have joined NEC, have been known about me. I think there are 3 or 4 people who joined NEC because of me, and I'm very happy to know that. so the seeds that you are planting that is achieving results, and JAXA, the manufacturer. So these people will continue with this project going forward. But for the young technicians from NEC, if I could have words of encouragement from you for those people, well, there is really nothing for me to say. Perfect, that's all I can say. I'm just going to disappear from here.
Target marker was shown earlier. Target marker. So you put your thought and feeling into target marker. On the outside, baseball leather type of film is over here. So 180,000 people, their names are contained, and so their names are definitely included in here. So thanks to the guidance from all the relevant people. Target marker, now Ryugu has 2 target markers, and they will stay inside Ryugu. Up until will they be there? Well, target markers will be there, but maybe the surface will no longer shine after 1 year. That can be a, say, memorable item in the future. And I received also one email, and you also paid homage to some very charming shrine. But what's the origin of that name? But before talking about that, let me say this. When I studied space exploration or asteroid was back in 1980s, in the late 1980s. At the time, the number of asteroids was very few. As you know, asteroids, even when you use a bioscope, it shows only a very, say, light dot. So now you see more and more asteroids. Hundreds of thousands of asteroids are now found. What I thought about first, how we should go for the exploration for asteroids, because there are so many. If you just cover 1 or 2 asteroids, is it really meaningful? So since that time, telescope was used for observation. So the light dots colors were observed. In the spectral, so the reflective spectrum will be checked on the surface. So the light is received from the sun. So there are many different reflections. You check the color of those reflections. In that way, so spectral analysis are studied from that point on. And with that, a large number of asteroids were classified or categorized. That work has been done. By now, they are divided into small categories. Spectral types are now many, with many different shapes and others. So they are very much subdivided. But broadly speaking, types are S-type, C-type, M-type, D-type asteroid. So those are the types, broadly speaking. Further, of course, further classification are currently being done. At least at the time I thought that the spectral type asteroid and representatives ones should be chosen to observe one by one. Then at least 4 types can be covered. From those 4 types, representative asteroids should be chosen. Then, at least minimally, the asteroid's overall picture can be understood. That's what I thought about. So, what are assumed to be asteroid samples are many on the face of the Earth, that is, meteorites. Particularly from the South Pole, there are many meteorites that were found there. And a large number of meteorites are also classified into many different types. And then we have some samples from the asteroids, we could say in that way as well. So we can make comparisons with those meteorites with these samples available for Hayabusa. So we can say link those different samples. But actually, there are many differences, of course. But linking those samples was one idea. So when you think in that light, then asteroids, it'll be very difficult to get to asteroids. But the asteroids that come close to the Earth, there are many spectral types of asteroids. Therefore, at the time, rockets were not so powerful at the time. So scientific significance need to be found in the such spectral types, asteroids and meteorites, to be linked to each other. Among those asteroids that come close to the Earth have many mixed types. So scientific significance can be found with exploration of the asteroids that come close to the Earth. That's how we studied. So initial Hayabusa is a S-type, that is Itokawa, that's right. This is C-type, Ryugu is a C-type. And the remaining is M-type, D-type. D-type means, which is quite often talked about, it contains a large number of organic matters. M-type is metallic. So metallic materials are contained. Iron and iron meteorite, that sort of thing. Of course, we should not be limited to Japan. We can work with other countries as well to collaborate with one another to push for such studies. Once we cover all those different types, then I think I can complete the whole loop, for my part anyway. Of course, deep space exploration need to be promoted further, and that should be also continue. And this Motoreki Shrine is the return shrine. So that I want the Hayabusa to be returned. It is located in Shiga Prefecture, close to Sakai. And so I pray for the safe return of the Ryugu. So I look for a complete success toward the end. In the project, there are some subordinates or co-workers or researchers who worked with you, your disciples as well. So the collision science is very much explored. So do you have any advice to your co-workers or young researchers? So for my part, and I have been doing what I liked very much. And people liked what I have been doing, and they have been very much expanding those studies. And there are many people who are involved in that. So I'm very much grateful to all of them. So going forward, not just collision science and asteroids only, but greater challenges should be I think young researchers can challenge for a lot of new things. Dr. Ogasawara, from representing the manufacturers, what is the fun for getting engaged in outer space? Young people nowadays don't like to use hands because they can work on the PC, but they don't want to be down to earth, like making things or writing sentences. They don't seem to be good at it. If you are having that nature, then you cannot make things like this. Well, maybe if I say that, it's not so good for recruiting the young people, but something you should be down to earth. And trajectory orbiting calculation, that may sound look, but you have to repeat that process hundreds of thousands of times. And the solution may arrive at even out of that, but still it's not so much satisfying. But once you join a manufacturer, you find something, you make something, and then if you really want to experience that, you want to have that experience, please join NEC. So right in our background, and so all such great pleasure was enjoyed among all these people. I think that is a great thing. And so the people's will, that is the exploration activities, that should continue. So thank you very much, gentlemen. So those of you who are watching live broadcasting, there are some congratulatory messages that we have received. So let me introduce them to you. Hayabusa, in the first one, not just engineers and PR were involved in this, and the honorary professor Yasunori Matokawa sent a message to us, who was honorary professor at ISAS. Hayabusa2 members. So with the wonderful co-workers, you did a wonderful job. That should be a great asset for the rest of your life. This is a great achievement. I'm very much proud of all of you. So you should be very careful about security is the greatest enemy. And so you should watch out as well. So this is the second time they showed a peace signs over here. And this is the old picture of the control room. Dr. Yoshikawa, maybe he looks very young. 2 years ago, in the control room, there was the renovation of the control room, so it's different from the Hayabusa days. In Hayabusa films, there is a set which is very different from the current control room. It's now a control room is very functional, so people can now work in a very functional environment. So the new control room, how do you feel about the new control room? You experienced that. In order to work on major projects, that this number of co-workers is to be needed, which I came to understand very well. At the time, the rooms are divided into several spaces, but now I think this new control room is very good in that the communication can be easily done, as well as sharing the same screens. We all work on the same mission, and this control room is designated for that in terms of its design. And there's one glass. From this space, you can see the control room. So this was also newly established when the renovation was made. That's why we are making this live broadcast is possible. It's a W-shaped seat allocation, so tables are not just the laterally placed, and it is placed in a communicable way. And in the old days, there were only just a lateral table was laid out. So many things have changed. Control room has changed. Not just that, Hayabusa, the first spacecraft knowledge has been fully utilized to go for safe touchdown. The net broadcasting as well. At the time, there was hardly any voice communication. but the initial PR people work very hard, and therefore we can have a live broadcast showing the control room, which is a legacy from Hayabusa 1. The exchange center is also a new one as well. That opened in February last year. Usually there are exhibitions placed in the exchange center, so the center welcomes any visitors. In the old control room, there is some actual tables that were used in the control room are also placed in the exchange center. And questions on the Hayabusa2 were also taken in the exchange center before. So now we have time. We would like to introduce those questions to you.
Earlier, Professor Fujiwara mentioned that from the Earth, Ryugu is just a dot of light. And is it really possible to visually see Ryugu from the Earth? And could you comment on how it appears to be from the Earth? Okuno-san, you have a gigantic telescope, so probably you have seen the Ryugu before. Well, from the Earth, it is about 22 light grade. So 22nd light grade is something it is very difficult to visibly see from the smaller commercial level of the telescope. This is very dark. You will not be able to see with your physical eyes. You need a very large telescope to be able to see. But you could calculate the position of Ryugu. Well, this is a great opportunity. So can you pull out the location of Ryugu today? We are showing the direction of an antenna which is directed to Hayabusa, and we are communicating with Hayabusa as we speak. And this is the solar system looking from the north area. We're in order to show the relationship, we show Sun, Earth, and Ryugu. This is the position of all these related position, and it is far away than the Sun, and 244 million kilometers is the distance between the Earth and Ryugu. And this is the light speed, and radio wave based time required for communicating with the two locations is about 13.5 minutes. Today, this is the daytime, so therefore the sun is shining. So compared to the sun, it is 40 degrees toward the west. So that's where Ryugu is located. Moving on to the next slide, Dr. Sawara is showing the number where 244 million kilometers. That's the distance. Yes, it is. And he talked about the accuracy of the touchdown. Now, going back to the slide, this is the daytime, so you will not be able to visually see the stars because it's a daylight. However, if there were no air, and there will be many stars, and here is the sun, and 40 meters right-hand side of the sun, there is Ryugu. Now, this is a small asteroid, so therefore the time by time the location will be changed, and Ryugu is one of the asteroids near the Earth. So if you're trying to identify the location of Ryugu, probably 40 degrees to the west from the sun, and if you could give cheers to that direction, that would be great. I've been in this operation quite often, and this is a very close. It was initially 300 million kilometers, and it took about 27 minutes. So current 13.5 minutes is very close, in my opinion. So I'm losing the the common sense because we're working in a very big scale. Now later during the winter time, the 4 engines will be operated, and the Hayabusa2 will be coming back, but all this distance in the air between will be the obstacles, and we will have a very difficult time for the operation return. So light seems to be very slow, so light minutes and light hour. I always hope that the light could move even faster. Here are some questions regarding this topic. When Hayabusa2 will be coming back, but the winter, is that going to be the winter this year? Well, until the winter this year, Hayabusa2 will be staying on Ryugu, around Ryugu, and then ion engine will be ignited, and after that, in the winter of 2020, toward the end of the year 2020, the Hayabusa2 will be coming back. So Hayabusa2 will miss the Olympic Games in Tokyo. Thank you very much for the question. Could you pull out the monitor of the control room? Now then, in the studio, we have President Kuninaka. So based upon our great excitement, could you comment on that? Yes, going back to the slide once again, and this is the future plan for ISAS, and we'd like to have a fleet of deep space, and that's our plan, deep space fleet. So far, we've been operating on the standalone explorers and try to maximize the impact and outcome. However, going forward, we'd like to use multiple numbers of explorers spread around the solar system, and we will integrate the data obtained from individual explorers so that 4.5 billion years of history of the solar system will be explored and discovered. And we'd like to identify the origin of life. And in particular, in ISAS, what we are paying attention to is the material transfer among the solar system, particularly the movement of water and the organic materials. In the location near the sun, there are Mercury and also Earth and the Venus, and after that, and these are the carbonious planets, and after that there are more planets outside based upon the metal. And after formulating the planet, the Jupiter and further out, there are the gasified air, which were delivered from somewhere else. And where that come from? Maybe that will be asteroid, or maybe the comets, or the dust in the space. That there are snow lines where the gaseous materials are to be brought to the Earth or the Jupiter at a later stage. So that missing ring will have to be explored, and that's a scenario for our exploration. Particularly, what is important is the sample return. Bringing the observation equipment in situ, rather than to capture data from far away, we would like to bring back the samples, and we will use the highly accurate analytical devices to analyze the samples. Hayabusa first one brought the samples to the Earth, and the current Hayabusa2 will be bringing back the samples in 2020. And in the future MMX, which is the Mars exploration mission, will be 29 that the sample will be brought to the Earth. So every 10-year period, on a regular basis, we will be able to bring the space materials back to the Earth. So it will take 2 decades and 3 decades, and such a big agenda where we are proposing to the world at this point. And therefore, I would like to mention that the samples that were brought is by Hayabusa 1 is the rock-based material, S-type asteroid. And what we are working on is a carbonaceous materials for type C. And if asteroids were to be explored, there will be the D-type in the future. That will be more complicated in terms of materials and composites. And every 10 years, we will be able to bring back such samples back to the Earth. And we are proposing from ISAS so that the scientists all around the world will be able to prepare for such grand mission. Next page, please. Now, as is mentioned earlier, Hayabusa 1, Hayabusa 2, as I mentioned earlier, and after that, this is MEO. This is the Mercury Explorer that is launched in 2018, and toward the Mercury, the journey is ongoing as we speak. And SLEM, the pinpoint touchdown on Moon, the SLEM is now under development as we speak. And fly by to the asteroids and analyze as we speak, and also the orbiting around the Earth so that we will try to go outside of the gravity area. That's Destiny Plus. And the exploration to the Jupiter, this is a joint work with ESA, where we have JUICE, a Jupiter Icy Moon Explorer. And in JUICE, the Ganymede, which is the icy moon of Jupiter that we would like to explore. And here's the Martian moon's exploration. And in Mars, there are Homos and Deimos. There are 2 moons, and either of them that we are going to land and we will sample, and in 2029, we would like to return to the Earth. So far was the solar system exploration plan, but for this page is to summarize the broader space exploration, particularly the X-ray range of the frequency, where we are very good, and currently we are exploring the CRISM telescope at this point in time. And Spica, Lightbird, and Small Jasmine, we are preparing for such projects as we speak. And now a single frequency particularly be focused upon so far. However, we use multiple frequency. For example, the pulse, the infrared lights and visible lights and X-ray. We cover all kinds of frequency. So 13.8 billion years of the lives of the space where we'd like to explore in our project. And of course, there are the space assets such as satellites. However, that's not all. We will collaborating with the observatories on the Earth that we'd like to compile these projects in the future. Now, being a part of the space planning, what is important, being asset is CRISM, X-ray analysis, and X-ray imaging and spectroscopy mission. So that is our plan going forward at ISAS. Thank you very much for your presentation. Now, following this presentation, I'd like to invite the members of the project to explain one by one. Professor, thank you very much. Now, from the project members, in the sequence of the launch timing, I'd like to hear the presentation. First one is, as the president mentioned earlier, the solar system exploration. And in that sequence, there are some which were already been launched. The Bepi Colombo project. Project scientist of Bepi Colombo, this is Go Murakami. Good to meet you. Thank you for introduction. My name is Murakami, in charge of the Bepi Colombo project. PP Colombo is the Mercury exploration mission out of the collaboration international. JAXA and European Space Agency, ESA, are jointly conducting this Explorer. We developed the Explorer together, and we are conducting exploration mission to Mercury. As you can see from this picture, JAXA Explorer, the MEO, Mercury Magnetospheric Orbiter, is to be used, and also ESA developed MPO, Mercury Planetary Orbiter. These two explorers are docked each other and launched together and delivered to the Mercury. So that's the mission. That was launched in 2018 from Guyana of France, and this mission is enjoying a long history so far. It's been over 20 years since the very start point of the preparation. And we are on journey to Mercury at this point, and this is operated quite smoothly. Our MEO is usually powered off, and it's dormant when it is delivered to Mercury. However, this month and next month, we will be checking the installations onto the MEO, and therefore we will check whether the devices are working fine or not. So far, the journey is okay. But this is going to be a very long journey. It will take 6 more years to be able to reach to Mercury in 2025. During that period of time, there are 9 runs of a swing by that we are being prepared. And the first one is April next year. That will be a swing by to the Earth, and that means that it is going back to the Earth just momentarily, and then it goes back to long journey to Mercury. And once it is reached to Mercury, all of the Explorer will be separated and start to orbit around Mercury. As you can see, for the Mercury surface observer, the geometry and the magnetic fields and internal compositions are to be explored. By investing in the Mercury, probably the planet Earth type of origin of the planet to be explored. And this is actually consistent with the objective of Hayabusa2. So this mission is very important for us. And MEO, our explorer, will be orbiting slightly away from Mercury and investigating into the surroundings of Mercury. Mercury is the planet closer to the Earth, and therefore the solar wind is the strongest among the planet in the solar system. In such environment, what phenomena have been happening is the type of exploration we would like to do. And at ISAS of JAXA, around the Earth, we've been conducting magnetospheric analysis on our side, and we bring this technology to Mercury. We excel in technology and bring our strengths to Mercury. So arrival is the 2025, and so many things have to happen, and therefore for the start of the observation operation, we are preparing as we speak. So Mercury is probably the hottest in my opinion. Are there any countermeasures that you took? Heat is very hard to deal with, and the solar irradiation is 10 times higher in Mercury. Therefore, the heat countermeasures put in place. For MEO, the surface material is very unique. Usually, Explorer have insulation material in gold color, but that material is not sufficient enough, and therefore, all the exterior surface is the mirror-based structure, so that we can reduce the penetration of the heat. And with that mechanism, we finally be able to explore the Mercury. So Mercury, Venus, and the Jupiter, and in particular, what is interesting in Mercury, I know that this is a group of Earth. However, for the other Venus and so forth, Mercury is much smaller. It doesn't have much of air around the planet. However, it maintains a lot of information at the very initial stage where the planet was born. Inclusive Hayabusa2, we are exploring the origin of a planet, and on the Earth, we almost lost all of the information. However, in Mercury, we have rich information in regard to the origin of the planet. By doing so, we were able to analyze how the rocks and the materials are being created. And that's our plan for Mercury exploration. Thank you very much. Next project, please. Thank you very much. Next is SLIM Sub-Manager, Professor Kushiki. Thank you and congratulations today. Could you elaborate on the project? So SLIM is the small lander explorer and moon, which is the Earth satellite. We would like to demonstrate the highly accurate landing technology. Kaguya of Japan and USLRO, there are the map information on the moon, craters and so forth on the moon. Based upon that map information, 100 meters diameter of accuracy of a landing is to be aimed at in order to demonstrate the accuracy of the landing technologies. So far, we've already targeting at whatever the landing points we would like to land it on. However, we are able to demonstrate technology to pinpoint a location where we wish to land. And there are a crater, and on the foot of the crater we'd like to land, and we are developing as we speak. This is exactly the know-how which we developed through Hayabusa2 will be used in SLIM project. Isn't that the case? What particular area of the expertise gained out of Hayabusa2 that will be materialized in SLIM? In ISAS, we have a lot of explorations and space science being implemented. In Hayabusa2, we have gained so many expertise which we learned out of Hayabusa2, and of course we will reflect that to SLIM project so that we will make sure that we can make great success in this mission. 2 meters and 3 meters diameter of accuracy is, of course, being achieved in Hayabusa2. However, with gravity, probably the accuracy of 100 meters in diameter accuracy will be very difficult. And gravity is 1/6 of the Earth. Compared to Apollo mission, for example, the downrange for the forward level, there are over tens of kilometers of gravity to be happening. However, use our imagery analysis technology and so forth, and we would like to achieve the 100-meter accuracy. No one else have challenged so far, but that's the level of challenge which we would like to do. Now, for the landing device, this is a very unique shape that you might recognize from the photo. Are there any comments in the shape? Our intention is to land on the foot of the crater, and Hayabusa2 we have experience of creating artificial crater using impactor and taking samples out of the crater. So that experience is fully used. Where around the crater there are so many different kinds of materials to be spread around the crater on the moon, and therefore we would like to try to capture such materials. I'm not sure this photo is clear enough. However, there is tilted, so it is the slope, and there are so many heterogeneous geography where 4 legs are usually installed in the Explorer and landing on the flat space, but that is not available for this area. We'd like to be able to land on this very difficult landscape, and that's the configuration reflected upon this particular Explorer. Moving on to the next project. Now, this is the demonstration and experiment of space technology for interplanetary voyage of Fathion, fly by and dust science. And this is Takashima, Professor Takashima. Now, Destiny Plus mission, I would like to elaborate. Destiny Plus is comprised of two major objectives. The first one is engineering objectives, using Epsilon rockets and try to materialize the Deep Space Explorer with a small scale, small sized and lower cost. So engineering technology will be demonstrated out of this mission. And while we are doing a demonstration, from a scientific point of view, we'd like to explore the Phaeton asteroid, which is the home grounds of Geminids, and we'd like to do a flyby to Phaeton and try to observe the dust and taking photo through the cameras. And why do we fly by to Phaeton? Organic materials are considered to be blown over the Earth from the sky, and that is the current hypothesis. And the dust's volume is actually 4,000 tons of dust are flying onto the Earth, and dusts are less susceptible to the heat and the cosmic ray, and all these dusts are flowing onto the Earth, and organic materials are included, and therefore this is a good candidate for the origin of life. And how the dusts are flying from the sky to the Earth, and we'd like to explore how dusts are flying around, and that's the meaning objective of a flyby to Phaeton. And the dusts, some are known, some are with known origin, and some are with unknown origin. And for the dust with definitive origin, we'd like to explore, and that's where the Phaeton is quite significant. So Phaeton is a very origin of Geminids, and size is estimated from the Earth is about 4 kilometers. However, when it flies to the Earth, it flies by very quickly. Therefore, the relative speed is going to be 33 kilometers per second with this explorer. And therefore, Hayabusa2, like Hayabusa2, we will not be able to land on this Phaeton asteroids, but we will only be able to fly by. And when we fly by, in that particular second, we will be able to use our observation equipment, and therefore we will be able to analyze the depths. And that's the ground objective of this program. So 33 kilometers per second, and simultaneous observation needs to be made, and that's a major technical acquisition that we would like to attain this time.
And the asteroids, they travel around the sun, but I think it's a good opportunity for this to come near, but that is also the reason for difficulties. So you're quite surprised with the speed. That's at 33 kilometers per second. It's very difficult to imagine that speed. So that entails a lot of challenges. Of course, we need to do observation at the right timing, and we should be able to leverage the technology that we have accumulated through Hayabusa and Hayabusa2 at JAXA. But we need to be able to track with camera the speed of 33 kilometers per second. This is challenging. And if we are able to capture the information, then other asteroid or for various celestial bodies within the solar system, we should be able to extend the observation. So in that respect, it's very important technology. So the bullet trains going in the opposite direction, that's far slower than 33 kilometers per second. So to what extent can you observe at that the speed is not going to be easy. But I hope that it will link to something more in the future. Thank you. So next is Jupiter Icy Moons Explorer, JUICE. And we have Mr. Yoshifumi Saito, the team leader, with us. With regards to JUICE, it is the abbreviation for Jupiter Icy Moons Exploration. Now, European Space Agency is taking a lead, but it is a global project. And we will, there are a number of observation equipment, and Japan will be providing a part of the observation equipment. JUICE will be launched in 2022 using Ariane 5 of Europe, and in 2030, so it will take more than 7 years, but in 2030 we are likely to arrive at Jupiter. After arriving at Jupiter, we will orbit around Jupiter for more than 2 years, and in the end, in 2032, we will enter into the orbit around Ganymede. And the Ganymede is surrounded by ice on the surface, but it is thought that there is a water ocean in the middle. And by observing Ganymede, we may be able to understand how the asteroids, how the planets developed, and we'll be able to see if there are the ocean of water outside Earth, and be able to see the type of changing environment that occurs in the solar system. And this will be the first the craft that will orbit around a planet. Jupiter is large, and so the Ganymede looks small because the Jupiter is so large. Ganymede is quite big, and it's one of the larger moons. It is not as big as Earth. It's smaller than the Earth. But Ganymede, there is a magnetic field, and that is similar to what we have on the Earth. And I'm sure there is gravity as well. That's right. Though it may be smaller than the Earth. So there is gravity, there is a magnetic field, and I'm sure that entails many challenges. So you'll be working with it. Because it has a magnetic field, there is aurora, so it should be very beautiful as well. And hopeful of obtaining beautiful images. And what's the biggest sales point, if you like, of JUICE project? Well, JUICE, we are going to icy moons, and icy moons is considered to have the water ocean in the middle, but one of the conditions for life form to be generated, there needs to be a water. And JUICE, we will be observing near Ganymede, and we can try to understand how the moons are formed, and so we may be able to come to an answer as to how the planets are created. And the Hayabusa2, we are hopeful of collecting organic matter, but this is also a matter of great interest in this project going forward as well. Thank you. There are many exciting projects lined up, and the next is the MMX project, Martian Moons Exploration Project. Yasuhiro Kawasaki is the pre-project team leader. So please explain the project in the brief. MMX, Martian Moons Exploration Project. And sample return technology that we have nurtured through the Hayabusa and Hayabusa2 project, we want to leverage this to work on greater missions. The Phobos and Deimos, these are Martian moons that we want to explore, and we intend to return samples from one of these moons of the Mars. And in terms of exploration of celestial body, and Dr. Kuninaka was explaining, but Earth-type planet, how did water or organic matter came about? So that will be a mission of the next step. So the movement and supply of these matter is what we want to investigate. And it's rotating around the Mars, and so this mission enables us to make various approaches to the Mars. And this will be the first mission to go to the Martian Mars and back, and this will be the great lead to a manned mission to Mars, and we may be able to collect matters from Phobos or Deimos, the Martian moons. And Japan is taking a lead in this project, but NASA or France or Germany, their space agencies also are collaborating. So this is a project that we want to realize as an international the project, and the launch is scheduled for 2024 right now. Mars is probably the most familiar planet to Earth, and so the next manned mission is scheduled for Mars. But despite it being close, there are many things that we don't know about the planet. Well, Mars itself is close to the Earth, and there are many similarities as well. So many explorers have traveled to the Mars and traveled around its orbit, but there are still challenges with the sample return. U.S. and Europe is planning a mission to return samples from Mars, but MMX will go to a Martian moon and will come back. But when there are meteorites landing on the Mars, then various dust may gather on the moon. So maybe there could be the pieces of Mars that we may be able to collect back from the moons. And so MMX that will target Phobos or Deimos, we may be able to understand the history of Mars, what it was like in the past, what it is today. In addition to the Martian moon, this will also contribute to understanding of the Mars. Can you distinguish between things that's from Mars or for Martian moons? Often the composition of materials are likely to be different, but it may be difficult to understand that based on the camera observation in situ. So they'll be quite significant for us to take this back to the Earth. And how were these Martian moons developed? Is also another matter. Maybe it could be a celestial body that was caught by the Mars, or something that collided with the Mars. May have gathered to form the moons. We don't know this yet, but by analyzing the sample that we bring back, we should be able to identify the cause. So despite it being familiar, we may be able to obtain hints to resolving many of the mysteries surrounding Mars with this project. Thank you. And last is the X-ray imaging and spectroscopy mission. And Makoto Tashiro is the project scientist of this project. Could you explain this project? Until now, we were looking at the planetary exploration in the solar system, but this one is looking at the stars or the galaxies far from the solar system here, and the galaxies are like the gathering of the stars, and In galaxy, it's a high plasma that fills the space between the stars or within the galaxies, and the highest temperature plasma sends out X-rays. So by looking at the high temperature plasma, you'll be able to understand what's there, what is being sent out, what has been accumulated. So that understanding that will give ideas as to how the stars are developed, and this satellite X-RISM is good at observing the high temperature plasma, and when you actually measure the energy, then you can understand the type of materials included in the plasma, and understand what elements there. And XM microcalorimeter, which is a new type of device that will be loaded. Astro H is also employed with this, and you can see the spectra on the spectrum on the right, and so you can see the sharp spikes, and each spike is showing the elements there. So this enables us to investigate the elements, and CRISM is employed with this device as well. By investigating here, we can understand what's being formed. And by looking at Doppler, we can understand the speed at which they are moving, the speed at which it projects out, and the speed at which it actually drops. So this is a new type of the satellite, and in that respect, the JAXA will be developing this. But for development or the mission, the conduction, we will have the support of NASA and ESA. We will be developing with 41 the space agencies, and we are scheduling to launch this in 2021 from Tanegashima. High temperature plasma, when that is observed, and that enables us to understand the source of galaxies. But when we understand the source of origins of galaxy, what can we understand? Well, space is considered to have been developed out of Big Bang, but Big Bang origin down the space has nothing but energy. And as the space spreads, we understand materials will form. And originally, it was hydrogen and helium only, not much in variety. But they gathered to form stars and started to create the carbon, the nitrogen, and so forth that enables formation of planets. And stars and the galaxies, as they were formed, led to the creation of these. But where, in what way, and how, and when we be able to understand or to investigate those aspects, and that is closely related to the origin of life. That's correct. And life form needs matter formed by the nucleus fusion, and I think these have led to the variety of materials being formed. It's important going to the terrestrial body within the solar system is important, but if we actually go afar, then we can understand the history long back. So it's quite important in that respect as well.
So everybody's gathered for the last 3 hours that we have been broadcasting to you. Pinpoint touchdown of Hayabusa2 broadcast. How was it? What's your impression? We had the first experience, and therefore I think I was able to calm a little bit more. But still, I was very much excited. The impactor worked very well as well. and so samples were taken from the crate, I hope at least. I serve as a supervisor usually, involving the activities of operation, but in this touchdown, but all that effort was for this preparation for touchdown. I think my efforts have been rewarded, I believe. Operation, of course, will continue, but I think I can continue to be working on this more energetically. I hope that today's event will be leading to the future activities, and I had a solid sense of that. There will be press conference from 2 p.m., which will be broadcast as well. So I hope you watch that as well. This is the third broadcasting for our part. In the first touchdown, the touchdown itself went very smoothly, more than we had expected. So we are not able to. We are not quite sure whether we're able to deliver that properly to people. However, all the important sequence was able to be delivered to you in real time, and spacecraft condition was also shown using a sketch as well. And I hope all these broadcasting would have been of a good service to you. I'd like to ask for your cooperation going forward. Okayama-san, you are involved in PR and science communication. The real-time space activities has been broadcast today. So there are children and the general public out there. So do you think, is this impacting to them as well? I think, yes, this will be conveyed to them. We can share this atmosphere with all the viewers, which is a great, I think, a pleasure as a science communicator as well. What is happening right now can be broadcast live. So I think we can understand this particular moment. We share this particular moment together. The people in the public viewing and many people paid great attention to today's event, and so I think we were able to broadcast feeling very strongly about the enthusiasm from other people. That live, there was still I think a wave delay by 13 minutes or 13 minutes 40 seconds delay. So, but at least it's still alive. We are researchers, and of course I'm a neophyte in PR, but we are sort of sowing seeds, and I think such activities can attract more researchers and people who get involved in this type of activity. I am interested in knowing how people are feeling behind the cameras. But thank you very much for supporting messages, and please come to the space site as well. And the following project members were able to explain the missions going down the road, and so the Hayabusa's immediate mission will be returned to the Earth. ISAS JAXA projects will continue further. So I hope people will support for that as well. We have killer missions as well. Both of us work like this on the YouTube, but our original work is to bring the spacecraft back to the Earth, and so we would like to deliver these samples to the scientists and the people on the Earth. So thank you very much for your support. Thank you. Goodbye. Goodbye.